seminarios de semestre del Seminario de Física y Computo. También, bueno, estamos celebrando el 7º aniversario de un seminario que pues, hemos tratado de llevar a alumnos y profesores de la facultad pues, temas a veces de física, a veces de otras cosas, ¿no? Entonces, para celebrarlo, pues, y como llegaba un invitado, el cual colaboraba, el doctor Patrice Le Gal de la Universidad de Aix-Marseille, él nos va a hablar sobre uno de los temas que trabaja en nosotros los físicos en flotación. Bueno, ahora voy a decirlo en inglés para presentarlo. This is the last seminar in the semester, and for this seminar, Dr. Patrice Le Gal will speak about some research about the lenticular vortex in the, for instance, the red spot of Jupiter, and also the Medis in the Mediterranean.
Okay. Thank you for come to ask this last one. I have to confess I'm a bit nervous because I worked this morning on my talk and everything was fine at 9 o'clock, and at 11:30 everything is exploding. and the PowerPoint didn't work with bad and so on. So I had, of course, you know how it is, you want to have a little color there and so on. You want it to be better, and the better sometimes is worse. But hopefully we have a copy on this computer, and I have also a copy on my there is a small memory board there on the computer with So this talk is about, as I said, about also to thank you for this invitation, but also for me to come. This is already 4 or 5 years that I visit UNAM, and I would like also to thank you for this collaboration we have today. And so just to present my work on this vortices. Just to start, this was an idea of field markers that I met in one of these APS meetings some years ago. And Phil is a professor of fluid mechanics in Berkeley University. And he asked me if it was possible to reproduce the red spot of Jupiter in the laboratory. Oh, okay, I thought it was a bit of a crazy idea, but he was yes, we can do something. And so back to France in my laboratory. So the name of my laboratory is IRFE. This is the Institut of Research for Phénomènes out of Equilibre. Okay, so we do fluid mechanics, but also some biophysics and granular physics, different things. And so I am a researcher at Universidad, and I work at the laboratory of Aix-Marseille University. So I went back to my lab, and I proposed to Michael Lebas, who is one of my younger colleagues in my lab, to hire a PhD student. Her name is Florian Robert, and we performed some experiments on that. And at the same time, Phil was computing some numerics with his own PhD student, and his name is Pedram Hassan Zahari. And now Pedram is an assistant professor, I don't remember exactly where, in the States, he stayed in the States. And the subject crossed back the Atlantic Ocean again to finish in Guadalajara University, where Anne Cross is a professor there, and Anne is a former PhD student of myself, but that 20 years ago. Okay? After she married a Mexican engineer, and she made a life there in Guadalajara. And they have, she's working with Raul Cruz, who is someone working in hydrodynamics and also in oceanography. And they hired a master student, Hector de la Rosa, and Hector also made some work on this lenticular vortices. And now we got a PhD grant from CONACYT for Hector to stay in Marseille under my supervision on another subject. So this is a real question of who knows who, and we are a big family, and it's very nice to have research we have to meet, we have to speak, we have to exchange ideas, and we have to visit the world everywhere. Okay? And so this is really the spirit of my visit here and of this talk. So coming back to Jupiter, I'm not an expert of Jupiter. Okay? Phil was an expert, he is an expert of Jupiter. And just to show you some images from the NASA of this red spot. So this red spot is a very big anticyclone in Jupiter, on the surface that we see on the surface of Jupiter. And Phil made some PRE analysis using the clouds in the vortex. Okay? So using the clouds, you can track them and you do a PRE analysis, and you have a map of the velocity in this big eddy. So this big eddy is 25,000 kilometers wide, like that. Something like a little bit more than 10,000 kilometers in the latitude direction here. So in fact, the Earth will go there. Okay, so it's as big as the Earth. So it's crazy anticyclone. And the velocity, you cannot really read the numbers there, are, in fact, they are in 79. That was a Voyager spacecraft mission. They were about 100 meters per second. Okay, so these are also very intense. And this red spot, in fact, is known from a long time ago, and we attribute this discovery to Hooke or Cassini, where they made some photo in 60-something, but pictures of what they saw on Jupiter. Let us remark too that 90% of the vortices, we say large vortices on Jupiter, 90% of them are anticyclonic. This is a remark that I made. This is an illustration that was done in 18-something, I think it's 1870. And it was reproduced in a paper by Hag in 61, where they think at the time that the red spot might be what we call now a Taylor column. That is, we know, and I will show you in the next slide how it works for those who do not know the Taylor column, but we can imagine that what we see is this thing, and the vortex can go down to the, we don't know if there is a floor, we don't know how it's constituted. Is it a thick atmosphere or narrow atmosphere? We still don't know that. And the Juno mission, which is up there now, will give some light on this thing. But there are two possibilities, in fact, to have these vortices like that. And this idea, in fact, lies on what is called the Taylor column. And the Taylor column is a very simple phenomenon. Imagine you take the Navier-Stokes equation. You say, I want a stationary solution, so d over dt equals 0. You neglect the nonlinear term, v grad v is neglected, and you neglect 2 over this cos 2. So the only thing that is left is the balance between the Poynting force, 2 omega across velocity, and the gradient of the pressure. And if you do that, you see because omega cross u has no component of the vertical direction, that dp dz is equal to 0. And if dp dz equals 0, after taking the curl of this equation again, you can prove that all the derivatives along z, all the field is equal to 0. That means that if you rotate the fluid strong enough, no gradient in the rotating direction. And there is a famous experiment that was done by G.I. Taylor himself, where he took a basin of water and he rotated this basin of water. You take a little object at the bottom of the basin, and there are two ways to do the film, and you can do it for students. It's a great experiment to use. Two ways to do it. Or you change a little bit the rotation rate of the flow, or you move a little bit. And I think this is the technique that Taylor used. There is put a thread on this little object there, and you pull the little object across the field. And what you see, in fact, is this kind of photos, this kind of columns that we call the Taylor columns. And these columns are very special. You see, as the flow cannot go over the object, because the d over dt equals 0 constraint. So when you have when the flow wants to turn around this object, he has to turn on the horizontal plane. Okay? And this is, in fact, what happens if you put a dye filament, and you want the dye filament to go across there, and it's not possible. Okay? The filament will just turn around this column. So it acts as it was a kind of solid column in the field. Okay, so you see at the time, in the 60s, people said, okay, we see something that might be the tailor column, and we just, maybe there is a mountain at the bottom, if there is a ground Jupiter or something, and maybe we just see the top of this tailor column. And in the 80s, one photo disappeared there, that's not important. What I wanted to say is that in the 80s, people reproduce what this kind of atmosphere, or this kind of climate we have on different planets. And one of the specialists of that is Peter Reed, and this is a photo that we have. So imagine you take Jupiter or any planet, and you look at this planet from the South Pole. So here you have a region, so it is a flat planet. Okay? You squeeze the planet. Here you have the pole, South Pole. Here you have the hot equator. So an easy way to do that, to reproduce this thing, is to take a basin. In the middle, you cool down the water. At the external part, you heat up this water, and everything rotates. And when you do that, I'll try to start it again, you see that indeed, you can reproduce this rows of vortices. This is called the baroclinic instability. And this row of vortices, in some conditions, and this movie, I don't know, yes, maybe this movie will show that, in some condition, you are left with only one single vortex. So this is very kind of red spot of Jupiter. Okay, it's a kind of column because it goes to the bottom. And later on, that was in the 86, I think it was still Soviet Union in 86, and people made a kind of similar experiment, but instead of using the baroclinic instability, they use a shear flow instability. So they had a parabolic basin like that here, and this basin, so this is solid matter here. This basin has two rings, one ring, which is in blue here, in the wall, and this ring can rotate versus the basin, and everything rotates. And you put a shallow layer of water there. See, that's the second thing here. And you see that here, there will be a shear, so vortices can be generated in water. And this is a photo from the top. And they have also, as in the baroclinic tank, they have several vortices. And in some range of parameters, only a single vortex can stay and remain in the flow. And here is the history of the number of vortices they have in time, just one vortex in the flow. So this is fine. It seems it's possible, if you use different kinds of instabilities in rotating systems, that only a single vortex can survive forever, or for at least a long time. That was the experiment that was done, and in fact it was inspired directly by Patrice. That was done in, not far from here, in Austin, in the laboratory of Aix-Marseille, with Joël Seminario. He was a postdoc, he's a French researcher now, he was postdoc with Sweden. And there, they use another technique to generate the shear. They have a rotating torus, field of water, and they have sources and sinks, a source and sink at the bottom of the tank. So you have this kind of radial motion, and when you rotate, radial motion, because of omega cross u, will make a force which is azimuthal, and so you make an azimuthal flow at the bottom. If you make an azimuthal flow localized at the bottom, you can shear it. You have an instability which is the same kind, in fact, as the one used by the people, I don't remember the name of the people in Russia, but generated in another way. And they observe the same kind of stuff. Okay, they observe that they have also, in certain circumstances, they have a strong, and this time was cyclonic. I read the paper again. They said that this vortex was cyclonic, was not anticyclonic. Okay? And that was confirmed by Phil, in fact. It was very hard for them to generate a strong, unique anticyclonic. Nobody knows really well. So, after this experiment, so where we are. What is fine is that we can have, as I said before, a single vortex which is selected by the pattern, by the flow. It is stable and it is long-lived. But it is easy to have a long-lived vortex if it is sustained by instability. Okay? If you put heat or shear, you can sustain vortices. And we saw also that it was possible, not always, but in many cases, to have anti-cyclonic eddies. And this, one of these big eddies can eat the others and remains alone in the flow. What was not really fine, in fact, is that these vortices are called barotropic vortices. As I said before, G over dz equals 0, so this is the definition of the barotropization of the flow. Okay? Nothing happens on the z direction. But, in fact, if you take the atmosphere of Jupiter, and the little dots there are the data that I took from handbooks that you can find on Jupiter. So this is, in fact, the pressure on Jupiter. So the pressure is a weak gas or a perfect gas with proportional to density. Okay? Like in the atmosphere, that is very heavy down, the pressure is high when you go down, and very low pressure, very low density when you go high. So it's the stratosphere. So is it possible that a vortex can be sustained in a stratified atmosphere? And that was exactly the question that Phil Marcus, who knew the results from Sweden and the others, he knew that they had barotropic vortices, and he was very embarrassed by that. Is it possible to have a barotropic vortex in a stratified atmosphere? If you look this a little bit more carefully, this stratification of the atmosphere of Jupiter, you can fit these data points by exponential law, and I found myself 27 kilometers. And what you can find in the literature for specialists of Jupiter is 23. So okay, that's good. Certainly something like that is the right number. And when you read things about the red spot, it's very difficult to know how deep it is, because the only thing you see is the top layer. But they can do a little bit of chemistry with the color of the clouds. And even this morning I checked the last papers, they are still people in chemistry, chemicists, they are still fighting to know what is this color and what is this product that can give this color and so on, under which pressure and so on. But apparently the red spot should be some like 50 kilometers, maybe 25, maybe 50. But in any case, it has to be constrained in the vertical direction. This is very small, 50 kilometers, compared to the 10,000 or 25,000 kilometers. So that's why we call these vortices pancake or lenses vortices, because they are very flat. So I will not explain that. So this is an experiment you can find on the web. My colleague, Michael Levars, and the student, they went to visit UCLA, and they had this kind of, they made some kind of student applications of these flows. So this is just a rotating flow, so you have to take, it is, the thing to play the record, how do you call that? Tourne-disc? You know what I mean? Turntable. Turntable? Okay, so it's a turntable. And you put a cylindrical basin of it, and this is plain water. And you put some dye, so you make a perturbation. This perturbation, the dye will expand. You make a Taylor column, as I explained before. Okay? So when you rotate, you want to be barotropic. Okay? Now, only stratification. So now in this experiment, the only thing we've done is salt water there, and less salt, pure water here. And when you put dye there, and the dye at a certain density, it will, of course, remain in a flat layer, trying to expand, okay, just because of the gravity force acting upon it. So now it's very easy to imagine that if you rotate a stratified flow, you have a tendency because of rotation to be elongated, and you want also to expand. Okay? And so this is what's going to happen. You have a kind of this flat vortex. We stay there at a given density, given stratification. So that was just fun experiment for students, just demonstration experiment. And what we did after that, before that, in Marseille, was to set up a rotating table. So this is, and I think you will understand even if it is in French. So we have a tank, which is a rectangular tank. This is 50 centimeter or 70 centimeter, 50 here, 50 here. And we have a kind of very small pipe here. We have a pump with a reservoir. And so we can pump in to produce something. What else? We have a screen here with dots, and we will use what is called the synthetic theorem method to record the perturbation in the density. Okay, so cameras, lasers, kind of easy experiment to do. And so this is a photo of this experiment here. Soil stratification, I can explain, but not maybe not now how you can get it. There is a technique called the double bucket technique, which is quite easy to set up, and you can have a nice stratification. So usually you put pure, very salty water at the bottom, pure water at the top, and you manage to have this kind of linear stratification between. And the vortices will be in this area there, and they can survive there at least. So these are experiments. So from the top and from the side. So you see we have a little part there that will push. We do the same thing as the first experiment I showed. We push inside some water with dye in it and also small particles. And you see as you push the water, it's because of the density it like to expand. As it expands, of course, the Coriolis force will act and will make it rotate. Okay, so you have a double thing. You have stratification will play a role with the density, and also rotation will produce. And you end up with this vortex.
But this vortex is at the center?
Yes, we put it at the center, and this is something we are thinking of. Sometimes, just to make it short, when you don't, in the theory, omega plus u can be anywhere on the table, except that we have a centrifugal force. And the isodensity are not really flat; they are a little bit curved like that. Okay, so but the rotation is still vertical. So there is a small angle, and this is called in meteo or in earth science the beta effect. So what is the effect of the beta effect? This is something we have not. Okay, so this is a PIV measurement map. So PIV, you have little particles, you have a camera, and you see how the particles will move in the flow, and you can extract from this PIV, you extract the velocity field. So you see that in the middle of the vortex, you have something which is minus omega vortex times r, not r, and a very small radial velocity in the And with that, we can construct our what is called the Rossby number. The Rossby number is the frequency of the vortex divided by the frequency of the table. But there is a factor 2 for the frequency of the table because of the 2 at the Coriolis force. So it is omega vortex divided by f equal to omega t. Okay, a little bit of equations. You will see this is very easy, and it's a very nice subject. I like this subject because we can, with very easy arguments, we can understand. So, we write down the equation of the motion on the radial direction. So, these are the linear equations which are linearized. And so dPdr is equal to what? This is equal to the Coriolis force here. And if I said that u theta is equal to omega r, so this is a solid body rotation vortex, if you want, I have this expression here. So dPdr proportional to r. dPdz is just the hydrostatic balance. So it is equal to minus j rho the tilde, rho tilde is just deviation versus the ambient rho. And so we define this as n squared, n being something that we call the universal frequency, which is characteristic in the change in density. Okay? So this n is equal to minus n squared, rho 0 z. Just a question that we call the n squared. This is a 0 to z. 1 over rho 0 to z. So this is the hydrostatic balance. So you see that, oh, this is very easy to integrate. You take this one, dp dz proportional to z, dp dr proportional to r. You can find easily by integration, but p is as a shape of the different p values are ellipses under this form there. And you can measure the aspect ratio of these ellipses. So you can measure, so this is a combination of the ratio between this term and this term, in fact. And an easy way to do it is to say, what is the dpdr? This is dp delta p divided by n, for example. What is dpdh? It is delta p divided by h. So this L there should be there. It is omega 0 f omega L. And you see omega 0 n squared multiplied by h. And with that, so you can calculate alpha, which is equal to the ratio h divided by L. And you find that alpha, the aspect ratio of the vortex, is simply f divided by n squared. So rotation, stratification squared times velocity, which is the vorticity of the vortex. Yes?
So the height, the z equals 0 when the density of this fluid is the same as the salt.
Yeah, right. Say that the center of vortex is equal. So this is our theoretical prediction. Okay? And we saw that we can have this kind of elliptic vortices. You saw them in the book. So we try to see if it works. Before to do that, just a number, very small, two different modifications of the theory. The first one is we add to the Coriolis term, we add one nonlinear term, which is the centrifugal force. You see, v theta squared divided by r. This is just the centrifugal force. And also, we can take into account the internal stratification of the vortex. Imagine the vortex itself is a little bit heavier at the bottom, denser at the bottom, at the top. So there is a stratification inside the vortex, a stratification outside. Okay. So NC, for example, NC is the stratification inside. And the theta here is rotation. So you transform a little bit the expression we saw before. Rho B will become Rho B times 1 plus Rho B. Rho B squared is exactly the centrifugal term, and you can do from us. And instead of n squared, we have nc inside the vortex, minus n squared minus n squared outside the vortex. So this is just a very easy extension of our theory. But from this extension of a theory, we see that for anticyclones, so Rho B negative, okay, in general, absolute value of Rho B is less than 1. That means that the table rotates faster than the vortex. Okay? Fast rotating mechanic, fast rotating table. This is usually done in experiments of the kind. But because Rho B is negative, anticyclones, I must have nc squared minus n squared negative. And that means that anticyclones must have a stratification less than the external stratification. On the opposite, cyclones must be positive. So this has to be the opposite sign, has to be positive. So stratification inside the cyclone should be larger than stratification outside. And we will use that after. So here are the experiments. So we measure the Rho B number. These are examples of the measurement of the Rho B number. So the Rho B number is there. So this is the Rho B number is the frequency of the vortex divided by the frequency of the table. Of course, it will decrease like that. And in fact, at the beginning of the experiment, it decreases very fast. Of course, because there is what is called the geostrophic regime to reach. Okay? You have all this turbulence you send waves, these internal waves in the stratified media. So at the beginning it is very abrupt and you have a strong stratification. But as soon as the geostrophic and hydrostatic balance is reached, the equation that we saw, they play together. Okay? If I want to extend, okay, if I want to extend because of gravity, because my own density, I have to rotate. Okay? And make a round circle because of these equations. And you can sustain the vortex. Much more for, you see here, thousands of rotation of the table, thousands of period of rotation of the table. Okay? Also, we can also make two nice pictures for different f over n. So that will give, this is I think alpha, and alpha at the beginning is a very elongated vortex, and here is a very flat vortex. So we would like to put everything in the same diagram, but before, this is just to show that we can measure very easily the shape of the vortex. So I recall that we have the pressure under an ellipsoidal things, and you see, because we put dye in the vortex, this is the white line there. So we, at time t equals 0, time t equals 0 is not the real time t equals 0. It is the time t where we decide ourselves that we are in equilibrium now. The vortex has not turbulence inside and so on. And so we say this t equals 0, and this is the first shape of the vortex. It was nearly circular here, and we let it go. And as the Rossby number will increase, okay, the aspect ratio will change. So in red, it is a prediction because of this equation, okay, where the Rossby number is a free parameter. Okay. At each time, we have a Rossby number, and the Rossby number gives an aspect ratio. And if you want more about it, if you want to conserve the volume of the vortex, you are constrained. So this is the prediction of the theory compared to the experiment. And this is also, so this one is the same, in fact. And this one is another one where we didn't stop injecting water in the vortex. Okay? So it's a continuous formation of the vortex. So the vortex will swallow it, its volume will be bigger and bigger, but you can correct this effect. And oops, and this is the prediction. And the prediction in blue and the observations are in black here. Okay, so it seems that our very simple balance between rotation and stratification, gravity, works fine. And in fact, we presented these results in a conference, and we met an oceanographer. And this oceanographer said, this looks like what people call medis. So maybe you can recognize here Spain, here, and Africa is here. And in fact, this is a numerical simulation done by people from Aix-Marseille in France, and their names are there. And these brown things there are vortices. From time to time, vortices are emitted just in Portugal, just at the horn of Portugal here. And the water inside these vortices is Mediterranean water, which is trapped in a vortex and is floating inside, I would say, the oceanographic of the Atlantic Ocean. So these medleys, as they call them, are very flat. So there is a description here. So the water from the Mediterranean Sea will flow down on the sea floor and will detach or make a vortex like that. And this is quite important because you can imagine you have all the bio stuff inside the sea or the salinity or pollution and anything is transported. And this, they can last for 4 years in the ocean, these measures. And this is a true measurement of, I think it was the density here, of the vortex here. And they know also that, and they can measure them when they do these campaigns in the sea, they can measure the internal stratification and the different characteristics of the medians. Okay? They know that the Rossby number is equal roughly 0.3, and that the velocity is about 10 centimeters per second, and so on. And they know also that they have an internal stratification. And you find all this data when you look inside publications from oceanography. So the idea is, oh, maybe everything can collapse together. Okay? From the lab to the medleys onto the graduate spot. Okay? And this is the final curve. Okay? The final curve of this study. This is so we recast the thing a little bit. Here is alpha, and we multiply by this n squared minus nc squared here divided by f. Here it is the Rossby number, which is here. You can take into account the 1 plus Rossby, but that's very small in fact. Our experiments are here. The blue open symbols there are the 3 vortices, are the 4 vortices, continuous injected vortices. These are the open symbols there. These are here the experiments on the vortices, the first one, the vortices that will finally disappear after 1 or 2 hours. Here, you know the crosses there, the different crosses correspond to different medleys, in fact. So we are really on the theory that we made. Here, this is the medleys. And the graduate spot is here. And this is the oval beam, which is another Jovian vortex also. This is another one. We have some data on it. So you see that we really predict with this very simple theory the shape of these lenses can be in the lab, which are very flat, small Reynolds number, to medleys, where Reynolds number is already very big, and even to Jupiter, where we have this graduate spot. Okay, these are the data. This is a photo of our experiment. Have we checked the time?
Oh, it's okay.
It's okay? And yes, so this is Orion, my student, former student Orion, and a rotating table, and you see this the vortex inside the rotating table. Okay, this is a movie that you can find on the internet. Maybe you know it, Perpetual Ocean, and it has a nice music that I can hear it. And this is a combination of measurement by satellites and numerical simulations. And you see, in fact, that the ocean, and I discovered that with this movie, not only medleys, but everywhere there are thousands of these vortices everywhere in the world. Okay? We pay attention to these eddies there, which are called the eddies of the North Brazilian current. Okay, but you see that everywhere we have these big eddies. Most of them are on the surface of the ocean. So we can look at the different currents and these different eddies. So that was the movie, and you can just say that. It was done by a joint project between MIT and GPL. And I don't know the names of the authors. They are not, we didn't sign them. But they said here that they present this movie to a competition, and it was not awarded. So I think this was very, very nice for them, because I think it's a great movie. Yes, nice for them to say, we lost, but okay. I will skip this part to go to the experiments, but just to say that, of course, that was what was the numerical simulation for the anticyclones from the Berkeley group. And they spent also some time doing cyclones, okay, in numerics. So, in fact, to do cyclones, you remember that cyclones need to have a stratification which has to be larger than the outside stratification. So how can we do that? You have a stratified flow, but a little piece of water there has to have a stronger stratification. This is very not easy to do. In numerics they can do it because they choose the initial condition. But in experiments, it's a bit more difficult to do. So to do it, and that was done in numerics, but also in the experiments, is to put a pipe in the stratified layer and to suck out a little amount of water. When you do that, you see that the isopycnol will be pushed closer one to the other. where at the place where you suck out the water. And when you do that, in fact, you increase the stratification. And it is what we did. So I will skip these graphs, which are not really mine, in fact. But you see that this is the stratification. These are the numerics. Okay? This is the stratification as a function of Z. And you see that with different conditions. You have here a kind of step which show that stratification is in fact greater. Okay? Because you have this density at a certain level, this density at a certain level, and you see that when you suck the water between, the gradient will be larger. Okay? So stratification will be strong. Okay, so we did that in the lab. So this is an experiment that was done in fact in Berkeley, where I stayed for some weeks. And this is PIV, reverse colors. And you see that I suck out the stratified water here around. You see that it rotates very fast here. And you have, this is the PIV map. And from the PIV map, you do exactly the same story as before. And what we observed is that we measure the density with a technique which is called fluctuation of the density, with a technique called the Sheeran technique, synthetic Sheeran technique. And in fact, these are what we measure. This is the d rho over dz. We can measure that. We can measure the d rho over dr, the radial gradient. And this does not correspond to the very simple map that we have for anticyclones. The cyclones we were able to create were a bit more complicated. And to fit this rho, we had to need a more complex expression, okay, where you have this kind of exponential, kind of a Gaussian function of radius, Gaussian function also of the vertical, and you have even a correction, polynomial correction for that. And this expression, in fact, is sometimes used by people from oceanography. This is where we have decided to take this crazy expression. And now we have 1, 2, 3, 4, and the Rossby number, 4 parameters to adjust to see if it can correspond to what we had in the experiment. So this is a fit of the parameter B. So the B, or this is the profile of the density, and this is the 0 dz, and at r equals 0 on the vertical, yes. And we see that this is what is predicted, and these are our experimental points. So you find the B coefficient, which is the curvature of the thing. And after you can deduce what is the K, and you can deduce what is the R, and you can deduce what is the L. Okay, and just to prove that this is not so crazy, this is what we did in the experiment. This is the measurement, and this is the 0 prime dz, the 0 prime dz here too, and at different time. And this is what the fit will give. This is not numerical simulation. This is just a fit of the expression we had before. Okay? This modified Gaussian vortex coming from oceanography. And you see that it is. We can say that this is satisfied.
There's always some kind of bump in the middle.
Yeah, because maybe I don't know. Maybe there is I don't remember the particle there. You know, this is experimental. You're right. There is something there that is neglected.
Mm-hmm.
And if we plot, this is the same curve as before, but this time for cyclone, you see that we have the same kind of thing that is respected. Okay, that was done, so more in numerics, and only a single experiment, in fact, on cyclones. And just to say something about the super certification that I said before. Imagine you have a stratified flow, like the atmosphere. If you have a storm somewhere, you imagine you have turbulence, you will mix up air or send the ocean. Okay? So this is very easy, in fact, to de-stratify a medium. Okay? You just mix up. Now if you want to super stratify something, you really have to put the other panels closer one to the other. And this is very much difficult to do in nature. And this is what we believe is the main reason why, particularly in Jupiter, we have much more anticyclones than cyclones. Because cyclones, if you want to have cyclones, you need super stratification. And there is nobody in the ocean or in the atmosphere with a pipe, sucking out the air or the water just to make a cycle. So this is the point I wanted to say. This explains also why there is this broken symmetry between both things. Apart from also different secondary instability that can appear and which are also different. Okay? And I will finish my talk with this study we made in Guadalajara. So remember I told you the idea started in Berkeley. We made the experiments in France, in Marseille, and I come back to Mexico because I like Mexico. So I worked with these guys there, and we decided, because of this perpetual ocean movie that I saw, we decided to see what about these floating vortices. So in a sense, they are a bit easier to make. Yes? It's a bi-layer, so you have imagine a salt layer that rotates. You take a syringe of pure water, you just push water on the surface. What's going to happen? And in fact, you do the same thing. Okay? Pure water will float, would like to extend on the top surface. As it extends, as it spreads away, it rotates and makes an anticyclone the same thing, the same way. So, and it is exactly, not exactly what happens in the ocean, but it is exactly what they observe. Okay? On the surface of the ocean, there are indeed many vortices. And my colleague Raoul Cruz from Guadalajara made a study of one of these particular vortex. So this is the one there. So this is the Brazilian or Venezuelan coast here. And these vortices, in fact, are moving towards north. And this is also interesting for Mexican people. Sometimes these big vortices, so they are born above the Amazon mouth. You see, the Amazon is nearby the equator, and you have a current arriving there. You can see the movie here, and the North Brazilian current will go to the north, will make these vortices, and sometimes these vortices can enter the Caribbean Sea, right? Where they die. You really will not escape. So this is one of my projects, or long-time project. I would like also to see when these vortices can enter the Caribbean Sea. And of course, there are many alluvium coming from the Amazon. So is there an impact on the biosystem in the Mexican Gulf? Is there also an impact on the number of fish? Is there an impact on the price of the fish? So this, I really, if there is someone in economy here who would like to help me to do that, I really would like to do that, to see is there an impact of these vortices on our everyday life. This is the meaning of economics. So this is a dream. I really would like to do that. It's still a dream. And so this is a vortex, and there are two kinds of data. There are satellite data where they measure the surface level of the ocean. Okay? And in red, it is because there is a bump. So an anticyclone is a bump. As normal, it can be a bump because as it has light water, it can float above the sea. Okay? So it is here. And we measure that. The point there are the data that they really measure on the ocean. So this is 100 kilometers. Kind of green. Yes, it is 225 here. 225. And the elevation, I can tell you, is 20 centimeters. Okay? On 200 kilometers, they have a 20 centimeters elevation in the center of this anticyclone. Okay, so this is also, so we have this kind of measurement with satellites, and they have also buoys that are left and that rotates, and this buoy can permit to calculate the Rossby number. Okay. So what I propose to these colleagues is, in fact, so to do this, you take salt water in blue here. We have fresh water, which is the one in yellow, pink in color here, and this is a warm anticyclone. Okay, it has this shape. you have also cyclones, why not? You have cold cyclones. So cold cyclones, you know, it's like a boat. You have heavy water here, and you have light water here. But heavy water has not a bend, but it has a deep. Okay, I don't know how to say it. You see what I mean? And so there is less volume here. But this thing is not stable, in fact, because you have heavy water. Locally, it's not stable. Locally, it's not stable to have heavy water above the light water. So this is not possible. But these ones are very possible, and you can calculate the solution of that. And the solution of that is not even here, but yes, it is even here. You see, this is the CR. So CR is the top surface, which is the expression you can get from just hydrostatic. This is the CR. This is the CR. And eta R is the shape at the bottom. It is given by that. Okay? So the first question, in fact, I had is it the same result that I will obtain if I do my theory? Okay, the theory that I presented before, so continuously stratified vortices. And it is exactly what we will have. And we will also do the experiment. So the experiment is, as I said before, you take salted water, here, blue, you have in dark blue here, the vortex coming from fresh water plus dark. Here, you have a bureta, how do you see that? That's Spanish. Bureta here, and we look with camera, lasers, and we make the study as before, and PIV data and so on. And so these are some photos from these vortices in green. So you see that as time is passing by, the vortex was like that, and it's flat and flat and flat and flat and flat and flat. And during this flattening, we would like to know if this aspect ratio respect the aspect ratio coming from the equilibrium equation hydrostatic plus geostrophic. So this is the variation of h, the depth, and I think the radius was maybe before. Radius. So radius will be radius is there, h is there, and PIV measurement at the top, 2 millimeters surface, and here we see the velocity profile as usual. There is a center which is not far to be a solid body vortex. Okay. But we have also to say that we have eggs. Okay, pay attention to that. This is a PIV map of that. So this is the Rossby number, as we said, it decreases very slowly. In fact, these vortices, just to be honest, are small, are a little bit unstable, but the eigenvalues are very small. In fact, this kind of study was already done by Paul Linden. This is a photo by Paul Linden in 1981. They made vortices like that, floating vortices on water, and they observed that in a certain area of parameters, you can have instability that breaks these vortices. And our vortices are here. They should be unstable, but very slightly unstable. Okay? And if we measure here, you see, if you measure the horizontal aspect ratio, that is the shape of the ellipse, you see that it started around 1, and finally, after time, it will go maybe to 2. Okay? So it will be slightly an ellipse and not a perfect circle. But that's not gravity for us. So we put together the data that they used at the time, the theory that they used at the time, and you remember I gave the expression for the C and the eta as a function of R. And you can calculate from these expressions, you can calculate the aspect ratio. And you can recast indeed this aspect ratio exactly in the same shape as before, which is here. Rossby 1 plus Rossby x squared divided by n squared. But what is very strange is you have to define what is n, this frequency due to stratification, and there is a length that appears, which is equal to h divided by 8. And I still do not know what is the meaning of that. H divided by 8 has a certain role there in the physics of these vortices, but except that we cannot understand that, we see that we we can define the alpha the same way as we did before. More than that, I think I will enumerate to the end. If you calculate, if you say that the volume of this vortex is conserved, as it is a paraboloid, okay, cylindrical paraboloid, Hr squared is conserved. So this is a new constraint. And if you take this constraint r squared with this one, you can prove that r, the radius, has to move, has to be to the power -1/6 of this term there. H has to be as this term as the power 1/3. And we've done that for the 5 experiments. We made 5 experiments. And you see this is the experimental data. We are not very far from the slope 1/3. We are not very far here from the slope -1/6. And now if we plot alpha squared as a function of the parameter, wow. Seems that the general scaling works, but we are very far away from our prediction. Our vortices are really too flat. We are missing something. Something is wrong in our theory if we want to compare to this simple theory. So to correct that, we realize, in fact, that these vortices were fitted by parabolic shape. But in fact, you see that the vortex does not have a true parabolic shape. It is more like a Gaussian shape. Okay? And this is a fit with a Gaussian shape. And that works really better. So can we do that? Yes, we can do that. Because vortices, which are Gaussian vortices, exist. And we know their formula, they are given there, studied by different people. So we take the rotational, the curl of the field to be under this shape. So v theta will be, v theta azimuthal velocity will be that. This is a comparison between the blue is experiment and green is velocity. Okay. Well, this is the vorticity, sorry, here. And the new parameter L, you see if you do R equals L, this term is equal to 0, so L is the point where the vorticity will go to 0. So in fact, these vortices are Sheldon vortices. Anticyclonic in the middle, cyclonic, the ring of cyclonic vorticity around. And if you do that, right, you can integrate the equation the same way we did before with a linear formula, but now it's Gaussian function, so it's quite easy to integrate. And you end up with a new expression for alpha squared, which is the same as before, but it has a term which is L squared, and this term 1 minus exponential this, that I call epsilon. Okay? So when the vortex is not in solid body rotation, but if we say it is a Gaussian vortex, we have an extra term that appears from the equation in the prediction. And if we correct, yes, the vortices, you can interpret them as we should. Okay, so I think it's maybe time to finish. I have several transparencies. I don't know if you want to stop there or go on to another one. Just to say that, well, the very last one. Just to say that we try to put on the same graph the vortices that we can find on the description of these vortices, the floating vortices. The same thing we did with the Méliès, but with floating vortices. And we studied 30 vortices, floating vortices from different places in the world. North Brazilian current, but also some African currents and so on. You see that the theory is there, okay, with solid body. Okay. Some of them are not very far away, but some of them are really, really very far away. They are really deeper than what it is expected. And this is still an open question. But last week I met there was some researcher working in atmosphere, and he said that maybe the beta effect can affect this kind of equilibrium we have in rotating or stratified flows. So we have in fact to look at the different vortices from where on the planet they are. And indeed, you can see, I just checked that this morning, really, but the F is very different. 2 10 minus 5 radian per second, which is the rotation of the Earth, multiplied by the sine of the latitude. Okay? And so indeed, you go from 2 to 15. Okay? So this is maybe a clue to correct this oceanographic data and to put them in the same field. And I will thank you for your attention. I'm sorry if I've been so long.